Okay, this is some of what's in Chapter 1 of Probability via Expectation from Whittle. Chapter 1 is called Uncertainty, Intuition, and Expectation. 1.1 Ideas and Examples. So, examples of where you would want to be using probability or where we make intuitive use of probability, like bank loans when banks are deciding how much money to let out and how much interest to charge on it. They're sort of having to reason about an uncertain situation so that they don't get burned. And the same thing with insurance premium, when to reap your crops if you're a farmer, just as examples. In 1933, Kolmogorov formulated or made an axiomatic formulation of probability theory, which is not the end-all, be-all, but most everything that's going on nowadays in some ways based on that. So in sciences, Mendelian inheritance, radioactive decay, these are things where we use probability models. The big idea is that probability theory gives us a rational basis for decision-making under uncertainty. Section 1.2 is the empirical basis. Probability theory is an attempt to give a quantitative basis to uncertain situations. The idea here is long-term regularity. So we know empirically that if you do something like tossing a coin over and over again, there will be like some kind of limiting value that the proportion of, say, heads seems to converge towards. So like this observation gives us hope of developing a useful theory of probability. The limiting value, it seems to be something real. So then the difference between and it's this something real that we're after and that we're going to be talking about. So if you're talking about proportions, this is like the idea of probability. If you're talking about long-term averages, this is the idea of expectation. But these ideas are interchangeable. It sort of depends how you code your sample space. So the whole idea, and I don't really get this yet. Hopefully I will at some point. He wants to derive probability from expectation. So expectation is taken as sort of more primal or fundamental, and then probability is going to fall out from that. Section 1.3 is averages over a finite population. So this is our big quote from here. The averaging operator is a positive linear operator satisfying the normalizing condition. So it's a functional of a random variable. And when Whittle is talking about random variables, he's basically talking about a mapping from each little omega within the sample space to whatever the outcome is of that thing that we're referring to. So the realizations of little omega are theoretical and specify the possible experimental outcomes, but they're like theoretically this is different from, I'm not really sure what the hell this is saying. Basically, you could do your experiment all day and you could suppose that you have an idea of like what the entire sample space is, but it's not necessarily true that your experimental outcomes will cover all possible realizations within the sample space. So I have another video up where they talk about the averaging operator, okay. And then the concept here of expected value in section 1.4, repeated sampling expectation. So the expected value functional is this thing that's supposed to capture what happens in this long run average. So it's the limiting value that we talked about earlier. And then he talks more about sample spaces, more complicated examples where the sample spaces can be infinite. Clearly, if you were going to measure temperature at all points in time over 24 hours. The temperature could be anything. There's infinitely many instances or moments during the 24 hours, so it's like your possible sample space for this experiment is really uncountably infinite. Even something simple like if your random variable is how many times you would have to toss a coin to get the first heads, your sample space consists of any possible positive integer, no matter how unlikely it would be to get, say, like 1,000 tosses before your first head. I mean, it's still a possible outcome, and as such, your sample space in this case would be countably infinite, but infinite nonetheless. Okay.